so we're looking at rotational motion, an object or objects that are rotating. We are only going to look at the rotation of rigid bodies. A rigid body is something that maintains its shape even as it rotates. So the meter stick stays as a 1 meter long stick. It doesn't change shape as it rotates. Okay? We'll look at hoops, for example. This is going to stay as a hoop as it rolls, for example. A cylinder, a disc. Now we introduced briefly a few concepts related to rotational motion. When we talk about the rotation of an object, if we talk about the distance it rotates through, we need to know which piece of the object we're talking about. Holding it down at this end becomes the rotation axis, the axis around which it's rotating. So a point close to the rotation axis isn't traveling very far as it falls. It's only traveling that little teeny tiny distance. Whereas a piece on the end has a large distance to travel through. So when we talk about rotation, we're not going to talk about traditional displacement as much. So displacement being the arc length, the actual physical distance in meters a piece of our material moves. Velocity, v, how fast that piece is moving. And the tangential acceleration, meaning the acceleration involved in speeding it up or slowing it down. There certainly is a radial acceleration for each piece on this meter stick as well. The radial or centripetal acceleration depends upon how fast it's moving and how far away from the center we are. Remember, the centripetal acceleration always points towards the center. The tangential acceleration will be tangent to the circle. So the tangential acceleration is related to whether or not our object is speeding up or slowing down. So as we look at this meter stick and it falls, the 50 centimeter mark does not travel through the same distance that the 100 centimeter mark does. Agree with that? The 50 centimeter mark here, its arc length has a certain value, but the end, its arc length is much bigger. The circle it's moving through is much bigger. As it moves from here to here, it moves a quarter of a circle, so 1/4 of a bigger circle is a bigger value. So the displacement of any piece of your object here is going to be different depending upon which piece you're talking about. The velocity of any piece is going to be different depending upon which piece you're talking about. To travel farther, this end of the meter stick has to be traveling faster. So the end of the meter stick will be traveling faster than the middle of the meter stick. And likewise, its acceleration will be different. But the meter stick, as a whole, moves through the same angle. So it has the same change in angle, a certain number of radians per second. It has the same angular accelerations. So we have the angular quantities that we're going to talk about. We introduced these before, but we didn't do much with them yet. So angular displacement, theta, the angle that your object moves through. So if you were to trace a line out to the piece of the object you're interested in and just let that line follow down to the final position, it's the angle that it makes. This needs to be in radians. And that's because of circumference. Circumference of a circle being 2 pi r, 2 pi is because of the radians. We can easily relate our regular displacement in meters to angular displacement, the angle. Angular displacement is the same for every single piece of your object that is rotating. So for every piece of the meter stick, every piece will move through the same angle. But they all have different actual displacements in meters because of how far away they are. The bridge between the two. The actual displacement in meters, the arc length, is simply the radius, how far that piece that you're interested in is away from the rotation axis, times the angle it moves through. So the two are directly related. Angular velocity. We use the symbol omega to represent it. It has units of radians per second. Angular velocity is the angle per time. Just like we had with our linear quantities, angular velocity is simply the derivative of the angular displacement with respect to time. Angular velocity tells us how many radians per second that object is moving through. There's a direct relationship between angular velocity and the actual velocity. And conveniently enough, it's simply multiplying by the r again. If you take r is the distance from the rotation axis. So here's my rotation axis. R is the distance from the rotation axis out to whichever piece you're interested in. Okay, if I'm interested in the 50 centimeter, the middle of the meter stick, then R would be 50 centimeters. If I'm interested in the end, then R would be 1 meter. Okay? So R in these equations is simply telling us how far that piece is from the rotation axis, from the absolute center of rotation. If your object is spinning faster and faster and faster, or slowing down, then it will have an angular acceleration. The symbol we use for angular acceleration is alpha. It's a Greek letter. The units of angular acceleration are radians per second squared. Calculus-wise, the angular acceleration is the derivative of the angular velocity with respect to time. And again, there's a bridge between regular acceleration in meters per second squared and angular acceleration. Now this is specifically the tangential acceleration, the one tangent to the circle, the one responsible for speeding up or slowing down your object. Just like we had for our linear quantities, if our acceleration was constant, then we had a set of kinematic equations. That we could use to relate velocity, position, and time to our acceleration. Now I guess technically we could make our x's s's if you wanted. Similarly, if we have a rotating object that has a constant angular acceleration, so it's rotating faster and faster and faster at the same rate, or slower and slower, so forth, then we get a similar set of kinematic equations. Wherever we have x, we put theta. Wherever we have v, we put omega. Wherever we have a, we put alpha. So there's a similar set of kinematic equations. We use them like we did the regular kinematic equations. If we know how fast something is rotating, and we know that it's going to come to rest, we could find the angular acceleration, for example, that causes it to come to rest. Or if we knew the angular acceleration, we could find the time it took to come to rest. Or we could find the angle it moves through totally as it came to rest. So we use them similarly to how we used the kinematic equations before. Now please keep in mind the angular acceleration must be constant for this to be true.